Yeah.
So I'm gonna start if you're ready.
Okay.
Just hold tight. I gotta go through a whole bunch of things, and then I'll bring you up here.
Okay, that's fine.
How do you pronounce your last name?
Odu. Odu.
Udu?
Odu.
Odu?
Anyhow, just call it. Yeah. Odu. Yeah. Anything.
Kenneth Udu.
Odu. Yeah, that's fine. That's fine.
Testing, testing. 1, 2, 3. Testing, testing. Can you hear me, Tavis? Testing. Is it working? Can you guys hear me?
Just gonna do a mic check, so can I get you to hush up and listen
Shh.
to know when the volume levels are good?
Listen to Tavis.
No, listen to Charles.
Okay, listen to me.
So people at the back, if you can give me a thumbs up when Charles is voice.
Can you hear me? Excellent. So some things to be aware of. This is being recording, right? Yep. Okay, so this is being recorded. So for people on the video to actually hear and understand the questions, it'd be necessary for you to go to a microphone and talk to there. So, you could yell it. Kenneth may remember to repeat the question so we could actually hear it on tape, but if you can, go to the microphone. Is it just one mic?
No, get a mic there, and then fence it to the back. Get a mic.
Excellent.
There's another one which we can pass in front.
Excellent. So use a microphone. A lot of these mics, like if you start talking, you do this, you can't hear it. So you need to keep it near your mouth so they can actually hear you. Just something to keep in mind. Okay, so let's start. I gotta look at my notes. I got notes. Oh, one more thing. What are we doing?
I'm just going to demonstrate something else you have to do with the mic. You've got to wait for me to unmute it. So a lot of people will take the mic.
Stare at Tavis until he turns the mic on. Just like death look. Excellent, excellent. Okay, so welcome. Thank you for coming. How many people, this is the first time you've come to a meetup like this? Raise your hand. It's quite a few. Okay. So first thing, thank you to Unbalanced and Tavis for hosting us. Second thing, so there are a lot of meetups related to this that occur on a regular basis. I'll just go through them, then we'll hear a bit about them. So one of them is a Kaggle group. Another one is a data science reading group. Another one is artificial intelligence in production. Another one is NLP and deep learning. So first we'll hear about Kaggle.
Hey, everybody. So I help organize a Kaggle meetup group. Am I not close enough? Okay. I help organize a Kaggle meetup group. We meet every second Thursday, and we talk about Kaggle competitions. If you're not aware, Kaggle is a website that hosts machine learning competitions. It's a very it's a very popular website for the world's best machine learning data scientists. So the winners of Kaggle competitions often end up working at Google or DeepMind, and that's Google, but they ended up working at a really top-notch company. And as a group, every week that we meet, we have one presenter that reviews a Kaggle competition and talks about the data, what the competition was about, and what the winners did to win the competition. So we get about 50 people to each meeting, and this ranges from beginners just starting out interested in machine learning to experts that are interested in what the best techniques are. So whether you're starting out or want to learn more about kind of the best techniques, please come talk to me afterwards or just come to one of our events. Thank you. 2 days from now, thank you, Alexi. 2 days from now, we're having Stan, who's at the back, go over a competition on camera model identification. It's an image-based competition where, I don't know much about it, but images.
So the use of something like Kaggle is that if you're first starting into this, there's so much you can learn by just reading books and reading papers and stuff like that. But it's useful to actually do stuff in practice. There's a different kind of knowledge you can gain. And Kaggle is useful for gaining that knowledge. Okay, so the next one is the data science reading group. Dave?
Do I still have to do the death stare? Yeah. Okay. So we also have a reading group that happens every other Wednesday. It's a partnership to the Kaggle one. The next one is a week from tomorrow, and it's on deep image prior, so a lot of deep learning and things like that. As Charles was saying, to complement anybody who's doing Kaggle competitions and learning from practical experience, that by reading you get to know the cutting edge research. You also get an overview of different areas. We do a huge mix of papers. Sometimes it's cutting edge stuff that's come out from, I'll say, DeepMind or Google or Alphabet and other places like that. And sometimes it's an overview in an established paper that's been around for a while. So it's a huge mix. There's people of all stages that are there. You get people that come and have no idea what the paper's about. That's often me. And then we learn from other people who do know what it's all about. You can ask questions. You can hear how other people are using it and their thoughts in this kind of area. So it's a pretty supportive place. And then we all go to dinner after. So,
which you might do after this too. So the reading group is great in that, like a lot of times when you get into these topics, it's like Dave was saying, it might be something you're not familiar with, but once you come to these for a while and you hear these topics over and over again, you start to pick it up. So the next one, none of the people organizing it are actually here, so I'm having to give a little spiel about it. So one thing, you learn this artificial intelligence, you learn machine learning, you learn data science and all that, but actually using it in practice is interesting. So there's another track to these meetups called AI in production. And what this is stories from people who have actually done stuff like this and talking about like the difficulties they went through, the experience they had, et cetera. There's one more, again, the people for this aren't here, but it's on NLP and deep learning. So what this seems to be is people are going through the Stanford Computer Science 224 course that's covering natural language processing and deep learning. So that's interesting. Okay, cool. So So on to the talk. So this talk is about time series. So one thing to consider is like, what's time series? Why is this useful? I guess in my context, there was a situation where, so there's actually a bunch of different situations. You think, okay, maybe you're in an environment that has an engineering team, maybe you're part of that engineering team, and you have a whole bunch of computers, and they're running and collecting data and stuff like that. So think it could be like the number of errors on a server, it could be like the lag time, or how much memory is being used, or how much CPU is being used. And all this is a time series, right? You can like graph this and see some kind of graph, and you might want to do things about that, right? So one thing, it could be that you detect anomalies, like, okay, well, usually this graph looks something like this, and something weird happened, right? And if you were sitting there looking at it, you could detect that, and you could say, hey, this machine's gonna blow up, let's replace it, let's deal with this, and not have to wake up at 4 o'clock in the morning, right? So for example, that type of anomaly detection is useful. There's other situations I've been in, for example, when I was dealing with kind of financial types trades, and you had a graph, and sometimes prices tended up, sometimes prices trended down, and you wanted to make different kinds of predictions to do trades. But one thing you'd want to do is, for example, detect a change point, because if something's trending up and trending down, and you're not able to detect that beforehand, or at least when it happens, then you lose all your money, which would suck. So there's lots and lots of instances where you want to use this kind of stuff. So anyways, Kenneth Odu, right, is going to tell you about this. Come on, Kenneth.
Okay. Yeah, I have it. Yeah, thanks for coming out today. So, my name is Kenneth Emeka Odo. So, just right after grad school, I was in the process of trying to form a company, so with some group of guys. And then there was a problem they were trying to solve. Then they want to predict some financial data, and then they wanted to use it's like something Bitcoin related. So they wanted to use some existing indexes to predict like the next index of their target index. For instance, you have like maybe what's it called? Something like this, Ethereum or so. And then there's all these Litecoin and Bitcoin and whatever coin you have there. So you want to have a kind of you want to combine all these existing indexes or their values to predict the next value of your maybe Bitcoin as your target, the next one. So and then I started doing some research, and then that was where I got into Kalman filters, and I realized that could be applied in those kind of scenarios. And then I also proceed to discussing a number of popular trends in time series analysis. So and you see how as we proceed with this talk. So okay, yeah, this is my outline actually. So I would actually go ahead, and I'm focusing on only two aspects of time series analysis, forecasting and anomaly detection. And then discuss some attempts we had to deploy this in service. And then even in the anomaly detection, we went ahead and tried to, like if you're tracking some events on Twitter, you want to know when something like anomalous happened. So we were doing some kind of social media engineering in that context, even though this company ended up crashing, the company we tried to form. But we learned some lessons while it happened. So well, it was really, really interesting. I was the data scientist in that team, and yeah, it was really good. It's a good experience. So yeah, my background, I have a master's from the University of Regina. I worked in the research, visual analytics. And right now I work for a company called PVO Systems. So we build smart meters, and so I focus more with troubleshooting network protocols, writing software for network devices. So so it has nothing to do with machine learning or data mining of that sort. So it's all software engineering stuff. So yeah, so this is just the goal of the talk. So what's forecasting? So forecasting is that, okay, I know what the past is, and I want to know the future. So you want to use the past you have to predict the future. And anomaly detection is you're given a data point. You want to know, is this normal or abnormal? So on solving this, you need to define what's normal. So, and that's actually the holy grail of anomaly detection. So what's normal? So because if you know what's normal, you can actually figure out what's abnormal by seeing deviations from your expectations. So if a data point doesn't meet your expectation, whatever that expectation is, it's an anomaly in that context. So it can have multiple dimensions based on the problem you're trying to tackle. So, and I actually proceeded in this talk to demonstrate a way of doing some of these using common statistical methods you have, and then proceeding to actually giving an exercise. So we will actually update, there's actually one of the papers I referenced, the algorithm is like a paper that was released in MIT labs. So as a group, it does some kind of time series analysis for univariate data, like one-dimensional data, just like one data spoon. So, but we will go ahead and extend it to work for multivariate traces. So, so that's one thing we do as a group. So, and yeah, so that's coming up right into this slide. So, time series comes in many forms. So, you can actually see someone in the pole vault jumping over the fence. So, if you have a trend or a trend line, and then you mapping each positions and the height this person is moving at each time. So you can actually get a time series with that. So everything around you could be time series. It depends on how you model a problem. So time series is the modeling choice. So in this case, this guy is just jumping across. So on a pole vault. So, and yeah, so also, if you go to a missile defense system, for instance, this is a third missile defense system. You can actually see, like, this is an enemy trying to launch a missile, for instance. And this is like some physics, like, oh, you switch on some kind of rocket, so you don't like burn this. So you move a bit before switching on those rockets. So now you're flying on the air. This is like trying to attack the city, maybe the city is on this side. So this is actually a time series now. So with time, it's also time series. So it depends on how you can model your problem. So, and this is actually like a missile defense that, oh, your radar just detected, oh, something is up there. And you want to like, okay, all your guys are in this container, for instance, in this car, and you want to launch a counter device to like annihilate the threat. So on this point. So why I put this example is I was discussing Kalman filters. And in a problem that may even look like this, Kalman filters are usually useful because you're doing sensor fusion. So, and yeah, if you understand what state space methods are, you can actually figure out the way. So, and I will discuss Kalman filters and then revisit this exercise, this problem, and try to explain my point. So, but now this may look like abstract concept. So just assume it's just one of those things. So, and then this is just like normal time series that we are used to. So it's just like a time trend of Bitcoin that as it fluctuates. So it's more like noise lately. So Bitcoin value is very noisy. So, and then I actually went ahead to show you why maybe some of your predictions in the financial stuff may actually not work if some conditions hold. And also, you can't do time series without handling stationarity. So, and we devoted some resources to trying to like explain more on stationarity too. But because stationarity is a very wide concept that actually you could actually write a PhD thesis on it. So, but we tried to do as much as we could within the span of this talk. So, yeah, so this was the goal I set out when I wanted to do this. I want to avoid anything that requires like huge computation, huge number of computation. For instance, a neural network back and forth, how's it called, backprop stuff, going back and forth will not suffice. So we want everything to work in real time. So, and that was some of the goal I set for that project. One thing is, so some estimates may not be so accurate, but if you're using something like Kalman filters, you can actually use the last correct value to correct your current prediction. So it's like 2 stages. So we get into that. So, and then, yeah, all the algorithms I'll be describing today are actually working in real time. So it's like linear, so maximum linear time complexity, and each operation should be constant time in it. So you don't want something that wastes time, takes multiple passes back and forth, seeking convergence. So, and there are some methods that do that. So, of course, there will be some trade-offs too when you try to do things in real time. But you try to solve a problem based on the constraint you've set for it. So yeah, so and then I decided to write two libraries. So one of them I named PySmooth. I don't even know why I named it PySmooth, but it's so now yeah I just put it up. So this is actually where I had the number of the time series I did here, and I tried to introduce one. Nothing is new in any of these papers. They all look alike. So I actually introduced a new one that I thought, yeah, based on what I read. So and then it's part of this too. So I had to make an ARIMA version that we know, incremental. So yeah, and I would discuss every aspect of it. So and then this, okay, then this one is the anomaly detection. So there are like two libraries where this talk is based on. So this thought is based on two libraries. Then the other part of deployment, that shouldn't worry you so much. So it's like I'll describe everything so you can actually have things that suits your own stack if you're working on it in production. So yeah, so something that should support both multivariate and so multivariate actually means having multiple dimensions. So univariate is having one dimension. So it's like if you taking the time at a single point. So maybe if you're taking the time and distance, then you have maybe two features, not features, yeah, two data there. So yeah, so let's this won't be okay.
I had to give him the death look first. So I saw that you had generative models on there. How were you, like, were you making use of the generative model at all, or?
Okay. I think that was maybe spelling not generative models. It was generalizable, something that generalizes.
Okay.
So maybe I would check the spelling.
Okay, cool.
Yeah. So okay, we can't do this without looking at the math. So the maths are quite very easy. So because I had a compromise. So this talk I had planned to give like a year ago, but reviewers actually rejected it for some conferences because there was so much math in it. So I had to remove it. So I was told to make things mathematics without math, so with stories. So, and that's why we make things very simple, simplicity. So, yeah, so as simple as possible. So this is just, okay. So yeah, this is just a time series. Time series is just like, okay, you have a data point, you have indexes, so you can put it in a list. So, and that your number of data in your list, whichever data structure you're using to store your data. No question. Yeah. So and then that's what I call time series decomposition. So it's like most time series you have is what I mean time series. Okay, this is like a single point. I is a single point. You can have many of them in a list. So most of them is a combination of a number of other factors. So it's like this first one. Okay, each of these points. You have this like a trend. This one is like a trend, and this like a cyclic component, and this like holiday component, and this like residual or noise. So what this trend means is like mean is usually trend most of the time. So and then seasonal component is something that has cyclic nature in it. So for instance, if you're modeling the days of the year of the week, you may actually figure out that okay, we always repeat Mondays to Fridays. So and then maybe some days are like not gonna be existing. Maybe those days are holidays. So, but even though you have this format, some of these may actually be zeros too. So, for instance, if a data point is on a like, if you're doing like a time series of amount of hours worked per day over a time. So, on the days we have Canada Day, for instance, that day will be zeros. So it's like, so those other variables will have their zeros. So this is like the kind of the latent, let's say, latent composition of this. So it's like the hidden representation. So and then they can also take multiple forms. So it can actually occur in like multiplicity of each of them. And that's why sometimes when you have some time series, you may want to scale things, like maybe logarithms or so, when you scale things. So if you put the logarithm, then you've taken it back to this format. So sometimes you have to scale some of your data, but using some functions like logarithm is one of them, and that has the property of like transposing this from multiplication to additions. So, and then there's actually, when you move towards the Drought models that I had to remove from the slides because because that would actually be a topic of its own. So I had to take that out. But I can explain some part of it. So it's like the Drought models, you're propagating your error in a kind of a residual from your initial prediction. So you have like a kind of a two-factor regression, like 2 layers, like arithmetical stuff. So those errors you propagate there has this kind of multiplicative components, like which one is like a standard deviation and the other is like a random variable. So it's but this is just to say one of those kind of situations where you can have them in practice. So but that's not the goal of this talk. But we will discuss some those pointers and give you some resources. So I don't want to get stuck in a rabbit hole. So I would rather refer to some sources for more information on some concept. So now you cannot. Then there's this concept that time difference and auto regression. So time difference is just quite easy. You can just plot a normal regression, taking the previous data and some scalar factors on them. So like fitting the regression on some history. So yeah, and then some residual value. So residual value is just the error between the real and the predicted value. So that's what this usually is. So, and if you see when we go to our this is exponential weighted moving average. So I introduced it after this slide, so maybe I shouldn't have done that. Yeah, but when we go to anomaly detection, you can see some of these kind of relations at work when you have a moving average, or as they call rolling means. So they have multiple names for the same stuff. So yeah, so then if you have this moving average too, this one is you're actually propagating over the errors. So and then you are like fitting a regression on it. So yeah, so and then there's a combination of these two processes. That's why you get the ARIMA process, as they call it. So yeah, so when you combine both of them, you get the ARIMA process. So the ARIMA process is like you want to consider some parts of the history of the data and some part of the history of your errors. So because you believe you have some information in it. So and now if you go to things like Drought models, you're actually propagating the variance in most cases, so which is a squared error in some context. So and because you may believe those have some kind of informative values in helping you predict your target variable, whatever that is. So and then if there's a little trick, you can convert this now to ARIMA by just using this differencing factor. There's always a seasonal differencing factor D, so it's related by this equation. So, and then we will actually move ahead to discuss how you could select good values for those parameters. So in something called the Bort-Jenkins methodology. So, which for me doesn't seem so different from the Occam razor we know of. But it's similar, I think so. Yeah, so the Drought models, actually, most of the time, you're propagating through your variances and then having this kind of, using the residual from your initial model and having these errors in a multiplicative context. So I saw that would bias the thought if I have to include this. So what I did is I provided a reference where you could, if you're interested in that, this is well explained and you can actually get all the gist on this. So you could actually, and they're very easy to implement. So since I have done something that looks a bit similar, the concept can still be applied to implement this. So this one's are also imposing constraints, like in these Drought models now, you're now propagating the variance and another standard deviation value too with some different weights on them. So that's also similar to the exponential moving weighted average that we will discuss in our anomaly detection. And these ones are just like constraining the weights using some kind of representations. So then here comes the gist. Why are we using Kalman filters also when we have other existing methods. So if you have a problem where you may have some measurement signals and you want to use it to augment your next state, so it's like you have something happening in an instance that, and you want to predict the next one that's not observable, but you have some other measurement that are observable at that time. You can actually use those measurements to augment your next state. So if I could quickly go back to this. So for instance, if you're trying to predict where will this missile be in the next second, yeah, and then you have maybe radars, your current radar gives you the position, like this is like your state, the position, the next state. And then probably you have your own other radars that are far off that may have some weak signal of this. So you can actually combine those readings together in a kind of a measurement vector to augment this state, which is the next position that you're doing. So that would be your and other stuff. So in time series, for instance, like trying to predict like the Bitcoin conditioned on things like, what's those things? Litecoin, Ethereum. So you have multiple of those. You can have all those as a measurement. And then the Bitcoin that you want to predict, you can use these values. So because you can make corrections. So because if the next value of Bitcoin can get wrong, you can make a 40 prediction, but in your next prediction, you will correct it. So it's like there's a two-step to Kalman filters, like predict and correct. So, and if you proceed in that kind of iteration patterns, you'll be making mistakes, but you'll be correcting your mistakes. And so probably you'll be moving like in a kind of, it depends on which you're doing, like something like your prediction will be wobbling a bit around what would be your expectations. So then let's go back to that. Yeah. So then, so now the crux of the matter is, how do you identify what are appropriate measurement signals? So that is domain dependent. So you have to figure that out. So you can actually see, okay, those are things that that may have, just for instance, a Bitcoin and those Litecoin, they could have some dependencies on them. So, but if you have more of those as a guide, you're more likely not to peg it on just only one thing that you don't know, that may just using only the state value to predict, where you may end up fitting some kind of transient spurious correlations, and that may hurt you. And then there's one very nice part, so like if you see the formulation of Kalman filters that we'll get into soon, those measurements help to capture the trend of those states. So if you look at this, so if you see this representation of data, you see this was a trend. So now the Kalman formulation, those measurements that you have helps you to capture the trend in the data. The trend is actually like the mean, actually. It's usually the mean. So, and then you can actually add physics. So for instance, if you're modeling location, like in Google Map, where they have, okay, you want to show how to, you want to stabilize someone moving on a path or on a Google Map. So you can actually use physics. You know, like people move in some kind of patterns, Euclidean distance. So you can incorporate some kind of priors using physics of what you know about this state. So this is the domain knowledge you know about the state. So it may be physics, it may be something else, but those are things you know about the state. So you can incorporate it actually in your representation of your Kalman filters. And that makes it very interesting to use too. So yeah, this is just a simple way of how things could work in the Kalman filters. So you usually start with the update, predict, update, predict, update. So you just go in that. So you continue in that route. So now this is actually like a representation. So you have this your state, and this is the previous state with a function that captures some parameters you may have. And then this is like, in this representation, this is a control variable. So that could be something else. Or usually in some implementation, they keep it, if you don't have any physics to introduce here, you keep it 0. So, and then this is your measurements. So this is this could be a matrix too that captures the relationship between the measurement and your states. And this is noise that you. So then, yeah. So this is just how it is. So and this is all similar. The state space method, and then it's actually the continuous. If you're very familiar with hidden Markov models, this is actually the continuous version of it. So, you have any questions at this point? Am I going too fast? Yeah, okay.
Just give me a second to turn it on, okay?
Okay.
Hello? Is this the classical format controls format x dot is equal to ax plus b and then y?
Yes, that's it. So it's just if you go to the Taylor series, you're just flattening things out.
Thank you.
Taylor series, yeah, that's it.
Hey there.
Yeah.
I just want a clarification. So the Kalman filter, is that to allow for the multivariate time series, or can you also do this just for like a univariate as well? Is it?
Yeah, you could have multivariate. So it's like you like there's some papers may not actually show some of these details. So if you have your states, this measurement, your measurement will naturally be even of a larger dimensions than your states. So in that case, this will not be a square matrix. So this matrix that maps both. So it depends on, and there's a little tweak you have to do in the implementation too. So like I think it's what they call it, the innovations part and the Kalman gains. You have to switch. You have to do some kind of augmentation, like those, change some part of the algorithms there. Yeah.
I had a quick question about the matrix, because it looks like an identity matrix, but there's an extra 0 column. Why is that there?
Okay. So this is just an example actually. So don't read much meaning into it. So
Okay.
so yeah, it would be a matrix. So they just wanna it to be something.
Check. Thanks. I understand Kalman filters can be used for sensor fusion. I'm trying to understand what would be considered a sensor in the case of your Bitcoin system.
So you have to understand it just like a group of data points with and that you record data points on them. Like so you see all those other variables are like sensors. So and then your target is like what you're trying to predict. So you want to predict and correct. So because you're better off if you're better off than just having only one source and trying those ARIMA on just only one variable too. So this gives you another option too. So it's like you don't only do one thing.
So let's say you're watching the Bitcoin time series,
Yeah.
and you made 2 different models to predict the next point. Maybe one neural network, maybe one something else. Are these 2 sensors that you can fuse this way, or is it that completely a different concept?
See, you don't see it as vectors. So if you say you have a measurement vectors, it could be anything. It could be some weak models that you're trying to combine into another good model too. So like there's actually a paper that you could use Kalman filters to do an incremental neural networks without that's training without bad propagation. So there's a paper on that. So most of those variations of online kind of algorithm training, so you could use that. So the point in that part of a Kalman filter is like you know the like immediate past. You want to predict the present. But in this formulation for forecasting, it's like we know the present. We want to forecast the future. So it looks a bit, I don't know, it's like it was some road version. So if you train like your model, so you say like the previous part is the current model you've trained, like you currently have. So this one is the last one before you make like your model. So like you combine Kalman filters on your training too. So there are many ways you could use Kalman filters. So this is just for forecasting.
Thank you.
Hello.
Yeah.
Okay, it's more like looks to me predictive analytics, right? So, my fellow was talking about the Bitcoin and the time series falling. Like, this could be analyzed in dollar or in any other stock market. But my point is, when suddenly like you are calculating based on the median of everything, based on the trend going on, and you're predicting the future.
Yeah.
So what will happen if something goes down all of a sudden? Let's say the today dollar price was one Canadian dollar equal to 1.37 USD. Tomorrow it fall down to one equal to one. So how do you predict, like instead of going upward and it falls down? So how do you predict that analytics?
Yeah, so there are some open problems in research about that. So there are degenerate cases, so where things can go off and not recover. So yeah, and then it depends on the Kalman filters. There are multiple types. So maybe you may not use a linear now. If your relationship is not linear, you have a degenerate case where things go off and never recover. But the point in Kalman filters is like you focus more on the long-term returns to, so you may lose now and then in the future, your model will get better. So like you learn your lessons the hard way. So just that kind of a concept. So you may end up learning your lessons the hard way. So you may suffer some losses now and then make corrections.
Yeah, just an example, like you might have observed last year recently, like there was a huge high and low on the Bitcoin part, right?
Yeah.
So it was hard to predict whether tomorrow it's going to be higher or lower. So in that type of time series, how do we go and analyze the future prediction?
Yeah, so I think we will get to that when we start analyzing stationarity and non-stationarity data. So where distribution changes. So and yeah, I think we will get back to that because some of those problems, if it's completely noisy, you may not be able to predict it. Still, and there's actually a slide I devoted to figuring out why things may go wrong, based on some literature too. So I actually devoted one slide to addressing those kind of concerns that you have. So I'll get to that in the future. I think the next 6 slides or so.
All right, thank you.
Yeah. Thanks. Okay, yeah. And then, so then I decided to discuss the different kind of Kalman filters that we have out there. So, so if you want to choose, there are multiple different kinds of Kalman filters, and you use the right one for your kind of problem. So, and then there's a problem if you can't figure out what kind of relationship your data has. You're better off not using a linear one, because if your data is non-linear, like, you can't capture linearity. So, but like in a case like polynomial, we know a non-linear polynomial is a special case of a linear one or so. So, well, yeah, that's just for polynomials. So I don't know what that functions. So yeah, and usually these are the properties of this kind of Kalman filters when you use them. So it captures the linear relationship, and it your prediction fluctuates around the mean and the covariance. And this is where you're having that problem I was telling you about. So you suffer from this eventual convergence where things may actually be going wrong now, but you have this long-term expectation that things will get better in the future. So you may suffer losses now and learn your lessons later. So it's, yeah. So this is just some underfitting constraints. So this is just like some of the implementations so this part is this PK is a covariance matrix. This H is that representation. That's that's this one. This is H. So and R is related to this. I think to this noise. One of this. That's this one. I think this is this one. Yeah, most likely. It's one of these two noises. I have to look up my paper, one of them. So it's related to the noise. So usually they usually assume it's a white noise. So it's like noise based on normal distribution with mean of 0, standard deviation of 1. So, and then this is a very important metric. This is called Kalman gain. So if you look, this is the like, it's related to actually that kind of exponential moving average. This is the amount of weight you place on recent items. So if you're trying to figure out something like a trend that changes so frequently, your common gain will be higher, because that means you want to put more weight on recent data and less weight on the past ones. So this value of T here, this one will be higher. So, and this is the covariance matrix. So this is just what's it called, the variance across the attributes, the features, not around the variance across the features. So and that's and they call this part the innovations, as they call it. So it's just the difference between your estimated measurement. So measurement times the state. Okay, it's the measurement error. So this part is the measurement error. So, and some people call it innovation. So it's measurement error, this part. Yeah. So, and then you initialize some values and put it in here. So this is just to show you how things work in it. So, do you have any question?
Okay. Just that H right there, is that like a hyperparameter, or is that decided somewhere else?
Which one is that?
The Kalman gain, the first step of the correction, you have P, which comes from the first step, and then you have the H matrix as well, and I guess R. How are those decided?
I think we'll go to already. You start with some values here, actually. So you could do two things. Like what I did is you could use, you get some samples first from your data and use that one a little sample to estimate those initial variables first. Or you can make them random too. So you can say that's like the tracking phase before engage in kind of a military contest. So like you track, and then that's when you just get in some data just to initialize your model, and then, or you start random and then hope the Bayesian formulation will help you out. So.
Okay, and just the R right at the end of the first equation, what is that? Yeah, right there.
Yeah, this R is a matrix that's related to the noise. I think it's one of the other measurement noise or state noise. I have to check that once more.
Okay.
So it's related to the noise. So it's the matrix of the noise. So yeah, so then we move to the extended one. Any more questions? Okay. So the extended Kalman filters, it's the attempt to create a non-linear Kalman filter by linearizing the Kalman, by linearizing it. So you want to linearize a non-linear equation. So they use Taylor series as usual. And yeah, so then there's a few things you should note here, because now we have to calculate Jacobians and Hessians. So it's just differentiating a matrix instead of like, so you have matrices and you're differentiating them with a function, with a nonlinear function. So your function should be nonlinear too. So, and they should be differentiable. So, but there's a quirk in this method, which like it's, because it's correct to the first order. It's like it maintains accuracy to the first order of the Taylor series. So, but then we now head on to and has similar computation like the uncentered Kalman filter. So this captures non-linearity too. So, and it's a little bit, so this is just the implementation. So we just added a few things. Yeah. So this part is similar to what we discussed before. And all these V and R are all related to the noise. So, and then this is an inverse of the noise. So, yeah, you initialize it. So they are quite similar to what we currently have. So, yeah. Do you have any question? So now, yeah, this is actually a better one. So the uncentered Kalman filter. So what's the goal on uncentered Kalman filters? So you want to have a more representative sampling of your problem space. So you want to take more, you have a data point. You want to select more data points that around your current data point that has more information about the current point you have. So it's like it's more like increasing the dimensionality if you look at the implementation. So, and the good aspect of it is it made the process more representative of the sampling that you could have. And there's actually an example that you could use. So, and the benefit is you avoid the use of Jacobians and Hessians. So, and that's where it gets the computational efficiency from. So you don't have to calculate those differentiation of matrices with a nonlinear function. You don't do any of those. So you could actually use any nonlinear function, even non-differentiable ones. So, yeah, so, and this is correct to the third degree, third order. So, and I have implementations of all this in my code. You could look it up. So once I will make these slides available, so you could also send me questions. Yeah. And then it has similar efficiency as the extended Kalman filters. So now, before I go to the next slide, I wanna give you, because I'm more of a kind of street fighting mathematician. So it's like I don't go for rigorosity of math proofs. Geometric proofs suffices for me. So I'm not trained in math. So it's like I just want to explain to you a few things about covariance matrices. So if you look at these diagonals, for instance, if it's positive, you lean this way. So it's like, so that means all your data you have at this point, like this point on this two-dimensional plane, if you take your data, all the data you have, subtract the mean from them, multiply it by the transpose of it, and you get one matrix that has this kind of component. So what you're trying to do, you're trying to figure out what's the spread in your data. So how does your data spread? Do you have any question? So I'm willing to go as slow as possible in these areas. Okay.
Or it was one slide back. Ergodicity, could you define that?
Yeah, it's more of the representation, more representative stuff.
Okay.
So it's all about, more representative nature. So, and this one, so for instance, now if you have your data point, so this is like, all these points, all these dots are actually data points. So like this dot I'm pointing here is a data point with x value of 5 and y value of 2, or 2.1 or 2.4. So this is, if you have multiple of these data, and you do the process I described to you, so what it tells you is, how does this data spread? So it's like a measure of dispersion in your data. So then from looking at this covariance matrix, you can actually tell the shape of how your data is in the input space. If it's negative, then it's leaning backwards. So if it's 0, it's just on the normal. So this is just a precursor to this one. So for instance, if you have your data point in this, so I want to explain how this works much better than other ones. So in this example, in this paper, they use the gold standard of Markov chains. MCMC. What's MCMC? MCMC is actually it's based on this law of large numbers, where you repeat an experiment multiple times, and then it averages to your expected likelihood also. So for instance, if you have a coin and you toss it 10 times, you may get 3 heads and 7 heads in one run. But if you repeat this multiple times and then average all your results, you end up getting 5, like 5 on one side head and 5 tails. So and then that's this. So this is like your initial problem space that has this property that I just described in the previous slide. So if you go through some transformation, whatever transformation it is, we are agnostic to that. So then this is actually what you expect if you do like MCMC. So let us assume this is this part. So we want to compare how extended Kalman filters and unextended Kalman filter works geometrically, because I told you I'm not a rigorous I'm not a mathematician. So then if you see this same stuff is what we have here. So now see the way Kalman extended Kalman filter is actually not actually fitting the distribution we have. So this ellipses we have actually, this ellipse that we have here is not ellipses like in the real sense. This is like a normal distribution, like what's it called? A parabola. It's like kind of a parabola that you look from that is circular in cross section, and you're looking at it from the top. So that's a plan. So that's what you have here. So you see, we are not actually fitting the distribution properly in the standard one. So, but in the centered Kalman filters, because of this extra data point we sampled around it, we are able to fit something that is very close to it without the amount of computational steps and sampling that you will get with a Markov chain sampling. So do you have any question here? So now the trick, if you want to do things incrementally, you want everything to work in one step, just one step. So this is actually the trick I used to convert the ARIMA models into an online version of it. So you want your linear regressions, or you start with some data, you get your parameters. So your theta is your parameters. So you want to add just a data and update your parameters and based on that. So it's like you don't want to repeat the entire regression. When you have data until time t. You don't want to repeat the process at time t.1. So what you want to do is like you just want to only use this single data point to update your model. So this is one lemma that I referred the paper to. You want to see the other lemmas. So this is what you do is like, okay, this is the first the data you have. You get and you project your errors, and then this part is your covariance matrix that I explained to you. You have a data point. You subtract the mean from it, just the way you do standard deviation. So you subtract mean from standard deviation, and so now you're trying to do this same stuff when you have multiple dimensions. So it's a measure of dispersion. You want to see the spread. Oh, okay. Yeah, you want to see the spread in your data. So, and that's what this is just doing. So you want to extend this covariance matrix when you have only one data point to work in an incremental manner. So you will see where that helped us in our ARIMA model too. So this is just an identity matrix. And then this is a scalar value on below. So this is a way of extending it just based on one sample. And then you update, this is your parameter here updated. So there are some implementations I would share later, so it's up there. So but now you understand how this operates. So do you have any question? Yeah, go ahead.
How do you gonna optimize the data loss in this case?
That's what this does from this lemma, actually. So this is what this does, actually. So what this is doing is you're calculating your residual. So this is quite easy to understand from this, from looking at this. You see, this is just the prediction of the next value you have. And you're subtracting it from the current input value of x multiplied by your theta value that you want to update. So you want to get some kind of estimation of error. So at one data point. So that's to do online, you have to make everything work in an instant. So you don't have to do anything. You don't have to go double passes, just one pass.
Okay.
So do you understand? This is like loss. This is the loss function. So you are propagating the loss. And that's actually the entire goal in this entire time series. They either propagate the loss, propagate the variance, or if you go to higher moments, you propagate kurtosis or skewness. So it's just, you want to propagate those stuff, those errors or stuff. So so you can add it to your estimation. Do you have a question, actually? Do you understand what I mean? Do you understand what I was trying to explain?
No, I'm a little confused, actually. Like, did you understood my question, right? When you have a scattered data point, right? So you have a data loss. Let's say if I give an example of this projector. So you are getting, in the particular dimension, you're getting this data.
Yeah.
So if the projector is scattered, so you will lose the data from the actual position. How are you going to optimize those data?
Oh, there are measures for performance. So we'll get to that. There are measures for performance, like you could use mean squared error or even R squared. Those are metrics you can actually use to compare your data. You can check R squared. So there's a kind of regression error characteristics that looks like ROC, like, like ROC, like receiver operating characteristics that shows the performance of your process in data analytics. So there's a regression version of it too. So you could actually combine those to actually see how you work, how your predictions are.
Okay.
So it's more of evaluation phase. So
Thank you.
Hi, just briefly, is RLS related to the ARIMA stuff you talked about before?
yeah.
So
So
this is how you implement it?
to make it online version, isn't it? To make it an
Ah,
online
okay,
version
thank
of
you.
it. So that was a trick. So yeah, so this is a combination of both of them. So all the places you
One more question in the back.
Just a quick question. When you mentioned to propagate the error,
Yeah.
is it that, or actually trying to estimate the variance covariance at each point and correct the next prediction?
Yeah, that's what this is doing. Yeah, the next one. So if you look in this part, so you're
So in
getting the
step
error
2,
in the
what
next-
you're getting is basically the variance covariance from the previous step, and then correct for the next prediction, right?
Yes.
Okay, thanks.
So it's more like Bayesian formulation. Just you update your priors and posteriors and something like that. So, okay, no question. Yeah, so this combining those two. So if you have a regressions where you have this ARIMA, the PD that I described. Oh, I'm going too fast. Oh. So how am I doing for time? Oh, what am I doing? Oh, okay. Yeah, so this is so when you have those equations I described to you in the past, so maybe I don't want to go that far anymore. I make mistake with this. So now when I get to, yeah, so I'm actually discussing, that I want to transform the data in a form. So this is like, this is the kind of methodology to choose parameters for your model, ARIMA model. So it's called Botch-Jenkins stuff. So it's like you start by estimating reasonable values for P is the time lag, is the lag of your prediction. Q is the lag of the errors you propagated, like you estimated the errors at those points. And then D is a different situation. So this is actually, in ARIMA, it helps us to attain stationarity, which I will discuss in the next slide. So, yeah, so then this is where your question came in. So there are many methods you can use for diagnostics to estimate how your model works. So these are like statistical stuff. So I like this method because it's much like a visual graphic. You can actually see something that looks like a receiver operating characteristics curve. So you can actually use that to see, and there's this mean squared errors, R squared errors too, that you can actually use as something to estimate how your model works. So you go and estimate some values for the PQD and check if it meets your criteria. If it doesn't work well, you change these values again. You understand what I mean? So like it's an iterative process, choosing these values for your ARIMA model. Okay.
Okay. So in this one, basically, you're introducing delay, right? So in
Yeah,
that,
delay. No,
yeah.
delay.
So
That's
when
the
delay
difference.
will come, the data will be slow, right?
Yeah.
Yeah. No, my point is like when there will be a data loss. So that means it's not delay, right? If you introduce delay, let's say if you're watching a movie, right? And if you introduce some sort of delay on that, you will see that the picture is moving slowly. But at the same time, when you push fast forward, the picture move fast. Basically, data is moving fast, right?
Yeah.
So in that case, like I was giving the example of this projector. So this projector was supposed to have spread the data on the square area, right?
Yeah.
If the data is scattered,
Yeah.
so that means the data is not coming onto the projector. It's moving into the outside of the boundary,
Yeah.
right? So that means we have a data loss for that. So how do we gonna optimize so that, because if we introduce delay, that means still the data is slow and it's not up to the mark.
Oh, I don't think this is delay in that respect. So this is just going back in time, like the kind of a time lag difference. So
Yeah, time lag is basically delay, right?
I don't understand what you mean by delay, actually.
Delay means you have a pause on the data.
Yeah, but that's what those lags are, actually.
Yeah. So
you mean you don't have those values, isn't it?
So if you are walking in a normal situation, right, there is no delay. But when you take small pause and then move, that means you are introducing a delay in the data.
Okay.
Right. So of course, in that case, you will not have a data loss because the data is slowly moving. But when the data is moving faster, it will be scattered.
Oh, okay. I understand your question. You are assuming we are considering
based on the graph you explain, right? You explain the graph how the data is scattering.
Okay, so in this context, you are assuming the rates of this data wasn't considered in this modeling. Actually, we assume that the data is at a constant rate. So what you are trying to say, like the variable rate, the data comes at variable rate. In that context, you have to aggregate your data first in some meaningful buckets. Like you can say every 10 minutes, you put those data together. So I understand your context. Your data is coming in at variable streams, like variable rates of arrival. Your rate of arrival is variable. So bin them into buckets, and then use those buckets as input into this.
Okay, let me rephrase one more time. Assume this is a projector, right? So this is a projector. The data is coming with a constant rate on your screen.
Okay.
Okay. If you expand the same data point, if you expand, the data will scatter, right, from the screen. So that means it was supposed to show all the data on the screen, but now it's showing on the wall. Some of the data is coming on the wall. So that data is scattered. Okay. So even though it is moving on the constant rate, but data got scattered. In order to, my question was, how we can optimize the data so that the data should not get scattered? Because you've shown the example of that graph where the data was scattering.
So what happened is we will discuss that over coffee, and we will get
Sure.
So I understand your question, but it will take a longer time to explain it. So. So then let's move to the next slides. Stationarity is actually, you have to understand this if you want to do time series. So it's like you want constant, sometimes some of these models require you to have constant properties over time. So it's like you want to have at each bucket of timestamp you have. So maybe you want to have the mean to be constant across. But there are many forms of stationarity. You could have it on the mean, variance, skewness, and other stuff. So now, why is this useful? So if you know that your data is stationary, you can actually predict around the mean. So you won't be far from the mean. So just like the future, it becomes like the present almost in some respect. So that's why most methods are actually using stationarity. So if you predict the mean most of the time on the stationary process, you won't be so far off. So, and it's usually mean reverting. So it's like at some point, the trend goes back to the mean. So, yeah. And there are many ways of converting the time series to that. So, and we discuss that in the next slide. So, and then all these words also, there's this Markov assumptions we usually have. It's like the future is independent of the past, given the present. So, in that context, it's like everything you want to predict in the future, you only use the current present. Because the current present you have already has some information from the past that you've accumulated here. So, yeah. So, for instance, going from one bot to the other, in this context, so maybe C depends on A and B. So, if you take the Markovian stuff, so it only depends on B. So, then you can have it to understand how those things work in these Kalman filters with the states and measurements. So you can have set of state and set of stuff and some prior probabilities of being in each state or being in each measurement. So if you have like a discrete space, but in Kalman filters is continuous space. So, but in this context, we don't want to go and make things more unnecessarily complex. So what this transition matrix mean is like, okay, what's the probability of moving from one state to another state? So, for instance, if you have your predictions, a group like high, low, medium, so what's the probability of moving from low to high, high to medium, so those kind of stuff. So that's what you capture. So, and then stationarity is something that shows up itself when you try to multiply by the transition matrix and it stays the same. That means your statistical properties are constant, even though you are shifting your data over time. So it's like this shift invariant, as they call it. Yeah. So then so usually in some case you may have some detrending stuff you may have to do, like removing the mean. So just subtract the mean from all the data points. And in some contexts, you may actually use like ARIMA models where the D difference factor helps you to normalize stuff. So yeah, and again, if you use a method that is designed with stationarity assumption on a non-stationarity assumption, you would have unrealistic predictions. So your predictions won't match reality. So yeah, and that's on tests. So the easiest test to do this is just to compare the means over some shift values. So there's a formal one, but those are for those who have time to look up. So this is where we normally use. So then you can actually just combine different shifts of the data and take some batches and then do that. So now this is where I want to go to. So stocks are very hard to predict. So and this guy was actually lamenting on LinkedIn of where it is to predict and even harder to profit from. So this is actually, if there's a concept in financial market called the efficient market hypothesis. So if it holds, then this means that that is identically distributed. That means there is no conditional dependencies between the present and the past. So you only have the present. So you cannot learn anything from the past. So, and this makes things very, very difficult. So, and we don't know when this will hold, if it exists in your data. If it exists, maybe in your stock prediction. We don't know if it will hold. So, but then efficient market hypothesis is very controversial in its right, in its own right. So, like you're saying, like all stocks are at the right price, but we know that doesn't hold most of the time. Otherwise, Snapchat won't be worth like 6 billion or so. So then you say you cannot. So if all are the right price, you cannot make any profit by buying some and selling later. So which is really wrong because sometimes you don't know the value of something until another thing makes that valuable. So and there are like dependencies too that we don't know. So and then you can only the profit you can make is only by sitting out risky investments. So in summary, it means you can't beat the market. So when you work on things like stock, you may need more than just Kalman filters alone. So you may think of adding some of your domain knowledge you have on the subject, causal inference. So because you don't want to end up fitting just correlation stuff. So you want to say, okay, does the price of gold influence the price of something over time? Maybe price of timber or so. This is an example. Price of precious metals are related. So you may want to peg things on that other ones. And even in that context, Kalman filters can also be of use too, because you can actually have those as measurements too, and your main target as your states. So that's your target variable. So you need a lot of complexities to attempt stock prediction. So and that's why some people may say they just try one method and hoping to beat the market. It's not that straightforward. So it's much more complex than that. So this is just some how the API of my system looks. So the init phase is just actually like you're trying to initialize some of the parameters by taking some existing samples like that you've observed. And then training phase, updates, predicts. So then the updates, predicts. So similar stuff. Yeah, those similar API across both. So then the other methods you could use. So the LSTM has time dependencies in it, which is very useful for time series analysis. But in that case, you still have to go to your backprop and other multiple. It's hard to actually get it to run in real time in online model. So, and then the hidden Markov models too are there. So that's actually the parents of Kalman filters and all those stuff. So like, if you have some kind of data where the time differences between things are like very sparse and it's very irregular. So you may actually throw out those time dependencies and just model it like a state space method with kind of Viterbi algorithm or so. So you could just do that. So since with some measurements you have. So provided those measurements will have information about the seasonality or some time stuff. So you could still be fine with that. So hoping that the Markovian assumptions of a model won't be too strong. So and then traditional methods, trees and other stuff. So I can't treat everything in one talk. So these actually, you can read those up in other methods. So then we'll move to the anomaly detection part. So do you have any question actually? Okay, maybe this part is more practical. So yeah, that we are done with time series now. So moving to anomaly detection. So yeah, so anomaly detection is like it's when you have an unbalanced data set. So that's when you have like more negative or positive samples or more than the other. So it's like you want to predict one instead of the other. So you want to predict the smaller components of it. Like for instance, if you have like a lot of news articles, anomaly detection may be, you can frame breaking news detection like anomaly detection, because breaking news are usually very minimal compared to the entire body of news. So because everything cannot be breaking news, but there are like very few breaking news and a lot of normal news. So whatever you define breaking news to be. So if you're CNN, maybe your breaking news definition is pretty coarse. So, and then the question is, what is a normal? What's a normal data? Because solving anomaly detection means you have to have an idea of what it means for a data to be normal, not as a normal distribution. So what's the expected data? What do you expect? So you have to have an idea of what you expect so that you can know when you see something you don't expect. So, and then in time series, there are multiple kinds of changes you look for in your data, in your stream. So this is what they call in signal processing abrupt transient shift. So most time series are like peaks, when something becomes so popular and then suddenly falls off. Or maybe a news article becomes so popular and liked on LinkedIn. People are just clicking it and liking it. And then suddenly the news is no longer interesting. So as frequent as possible. So you get some peaks like that. So and this also varies with the aggregation you set, how you set your number of bins. So and then this other type is distribution change. That means something became popular and lasted for some time, for instance, before it loses its popularity. So, and this one is just time data. So in our definition of anomaly, this is an anomaly. So because something happened suddenly and became unpopular. So you should alert the user at this point. Then this point at the beginning, this is an anomaly. Yeah. But after this point, you don't have to alert the user again, otherwise you're wasting his time. So you've alerted him once at this point and continued. And in this context, you don't have to alert at all because it's just like something is just becoming popular. Maybe your company has been bootstrapped and then you're like in Series D funding and then you're already having customer traction. So you know more, so the trend continues, upward trend. So you're at an upward trajectory, so there's nothing anomalous about that. So yeah, so there's actually a very good paper where this talk was based on. So then if you have data stream, so when you try anomaly, because we've been talking of time series, so time series, we're getting back to your concept, to your questions you had. So your data stream is data that comes in at some time interval, so it's by nature a time series. So then you have things like time and space constraints. You want to do something quickly, in real time, instantaneously. So and then you seek out online algorithms, things that work in real time. So then those online algorithms should have some properties like detecting concept drift. It's like detecting when the distribution changes suddenly. And so the previous distribution you knew is no longer relevant. So, but maybe your company was like a startup before, but now it has become a very big company. So people will discuss more about it on Twitter based on that change. More a small company, for instance. So, and then you should have some abilities to forget unnecessary history. Some history no longer reflects reality, so you want to forget the past to some extent. So, and then maybe you can also revisit the model. Maybe there are some parameters you had set in some part of the modeling. So you may want to change some of those variables because you want to the distribution has changed significantly, and it's so. Then there's also a time delay. For instance, if you want to alert someone to a fraud, a credit card fraud, you should design your algorithms in a way that even though your aggregations should be reasonably chosen, so that you can alert the user quickly when that stuff happens. Because your aggregation and other stuff determines how long it takes you to detect an anomaly and to respond. So you should actually also consider that when designing stuff. So then there are a number of, when handling data stream, there are a number of things people use. So like some people use a fixed window. Just like you can just have a batch. You say, we have this window just going through. And then we're making a processing on that, on the data we have in that window, that container or bucket or whatever we call it. So then the adaptive one this one is really interesting. So it's like you have two windows. And then if you check the differences between the two windows, and one is it hits a threshold you've set empirically, then you drop the older one and stick with the newer one. Okay, go ahead.
So the adaptive window would be really good for, let's say that in January you have low sales, but in December when it's Christmas, you would have a lot of sales. And every year around Christmas time, you would have a lot of sales. So you could use the adaptive window to actually set different thresholds for those months so that you don't get alerted. Is that what?
Yeah, this is just managing data stream in total.
Okay.
So we've not gotten into anomaly detection, but this is like things you consider too when you build these kind of processes. So I'm actually analyzing data streams for now.
Okay.
Yeah, so on the next slide, we'll show a working implementation of an anomaly detection.
Okay.
So that I'll walk through that.
Thanks.
So, and then sometimes you may have what they call landmarks. So if you have a way of figuring out important events happening in your data stream, you could save all the data from the point that event happened to the recent time. So it's like you have a lot of data saved. So maybe if you can determine the change when that stuff happened. And then the damped window is actually the common one that we will describe in our algorithm. So the damped window is actually part of what your Kalman does. So it's like you have a weight of a forgetting parameter. So you want to forget. What's wrong with this? So you want to forget part of. Okay, I'll put my hands this way. So you want to forget part of the future, part of the past. I mean, so by setting some weights, some scalar values on that. So that's what's like your Kalman does in the Kalman filter. And then the algorithm we will show you in a few minutes is based on this damped window. So this is one of those papers from MIT. It's an old one. It's 2000, so there's nothing new. This is not novel stuff. So, but statistics hasn't changed much over the past few years too. So all papers look the same. So I know Dave doesn't agree with that. so this is like this is like an exponential weighted moving average. So it's just about adding some parameters to recent values, forgetting parameters. So this is like your current mean. So this is what the recent past one. So this is your current data input. So you have these factors of alpha. So this is how much weight you put on your recent one. So this is like how much of it do you tip in. So that's alpha is the forgetting parameter. So, yeah, so this works, but when you have a high data rate, you are like you find it difficult to capture abrupt transient change. That's this one. So this one is very difficult to catch, and sometimes you don't even catch these ones, this kind of anomalies. So and that's where the probabilistic exponential weighted moving average comes in. So what this does is you add in an extra parameter of how you believe the probability of the current data point is. So that's the beta. You add an extra one. So this is the probability that this data occurred. So this is like the way I understand it when I read the paper. This is like your belief of the probability. So, but now the catch is anything that is monotonically increasing as a function could still work. So this is just an example they used. So what I mean by monotonically increasing is like something that keeps increasing, like because it makes sense for it to be monotonically increasing because you want to forget some of the past. So you don't want to. Oh, there. Thank you. So you okay, it's just like this data point is the immediate past, and this is the recent one. So you may want to reduce, you may want to increase this one and reduce this. So it's like you can't have it both ways. So it's like you want to maintain that kind of a filter that's reducing the value. Would I call that a low pass filter? Yeah, something like that. So you're like trying to dampen stuff. So in that case, it has to have that kind of property. So any function that does that should work. So now let's go to this equation. So we are based on, this is the Z score, this is like your input, then this is, your input is like your priors, and this is like your posteriors. This is your standard deviation. This is your number of training set. This is your index. So this is your probability. This is the next value you get in, and this is the next standard deviation that you obtain. So this is a Z score, for instance. So this is quite common. So on a normal distribution, so you want to have a standard score. So and this is like your probability from normal distribution. So you could also have any other distributions here if you know that your data follows that distribution. So you can treat things like that. So, but why people use normal distribution is because of the central limit theory, where they said most distribution converges towards a normal distribution. So now what this does is in this algorithm, they made a choice to set their weight vector when they are training it to be monotonically, is it increasing? Yeah, it's increasing, monotonically increasing. Yeah, it's increasing. So, yeah. So, same concept as I was trying to explain here. So, and then in this part of the equation is this part of this equation. So, during test time, they try to use this part. So, this is just a weighted moving average like you have here. So, this is a mean. So, this S1 is a mean too. So, you're just moving it. So you're trying to get the next estimate. And then this is what's this called? Statistics, expectation of the H squared. And then when you subtract both of them, you get the variance. So standard deviation is the square root of variance. So you take the square root of it. So what this does is you just want to use this new standard deviation that you get here. So at this point, and compare it with the threshold you've set for how things could, which values could be important. So I will show you a graph on how I can choose those variables. So do you have any question? So this aspect, these values we get here, is actually this this line I'm trying to rule here. So it's like, so now in a normal distribution, so you may have a threshold to say, okay, values on this part, maybe this may be normal, this part may be a normal part, then anything on this side or on this side is an anomaly stuff. But it will also, in this algorithm, it's symmetric. It takes both sides as an anomaly. But you can still customize that algorithm using these values of the X, the Z score, to actually choose one side. So you can actually set things to say, okay, you want only this side to be an anomaly, or the value is less than this on this part of the normal distribution. Or you can still set it on this other side of the normal distribution. So you can actually, your assumption is that all the values on this part of the graph are normal behaviors. Then all these ones on this beyond your thresholds are abnormal behaviors. So you flag those ones as anomaly. Do you have any question? So now the catch here is the catch here is that this is for univariate case. So, and if you see the goals I set for this talk, it should also work for multivariate cases too. So we have to do some tweaking to this algorithm to make it work for that. So, and that's where our group activity comes. So we want to go back and customize that algorithm to work for multivariate case. So manually. So there are a few changes you can do. So you just change this probability for normal distribution PDF to a multivariate case. So then these are like vectors coming in. Yeah. And then covariance matrices. So everything should, I think this is the major change you have to do. If you change this part to a multivariate stuff and then just obey the vectors as you move back. So you then get this value here. So, and then you use these same thresholds. So as normality stuff. Do you understand what I'm describing? So yeah, because this is a normal distribution that we currently have. So it's just based on, this is a very based on normal distribution. So it depends on how far you are from your mean. So if your mean is 0, so usually some models have like plus or minus 3 as normal values, and then anything beyond that is abnormal. So, but if you now use some of the Z scores to augment this stuff, you can actually have a one-sided anomaly or the other-sided anomaly. So that's just the goal in this part. So you can just make that kind of customization. So yeah, so then we'll try to deploy stuff. So well, and then we're having some issues. I don't want to have anything that's like AWS specific, or because you want to change something any day. So we're just playing with trying stuff out. We don't want to get tied to one vendor at that phase. So we just use a very basic Flask app, a Redis app, Devent app. So in those cases, and push this database then. But now that if I was building this right now, I would have done something totally different. Maybe try some time series table database that are currently available. Things like Apache, like what I use now at work. Is it not Apache Spark, and then this streaming stuff of Apache. I can't remember the name now. Yeah, Kafka. Yeah, we use that too. So, but that was what I did just after grad school. So I would have thought of using those two. So like those kind of applications, you have like 3 or 4 things on like a web server. If you want to optimize stuff too, you may want to use like a kind of caching server so that you want something to be responsive. You don't want, if you've done some queries before, because maybe some things look similar, you don't want to waste time and repeat it. So you catch stuff. And then maybe another server where you put some of your custom algorithms and your models for training things. And then maybe your database too. Yeah, so this is just a little bit of this very basic description of stuff like that. So, but then you don't need this sometimes too. So because there are many services we had then as we were building our startup. So we had many different kind of services, but I just combine everything in one chat. I don't want to do things twice. So yeah, then So you can have database for things like authentication. So for instance, if you're providing a service to user, you want to save user credentials in the database and metadata, subscription, managing limiting rate, how long you hit the database or application for that denial of service attack, things like that. So, yeah. So, but maybe if I'm using this now, I wouldn't have been using JSON here and there. I would have used things like protocol buff. And maybe I won't be having things interwoven like database. I'll use things like maybe Elasticsearch and use those web RESTful APIs. So, and then maybe I would have even be putting some version control on my models. So things are easy, because then we had a lot of issues reconciling one model to the other model. So there are a lot of version issues across. So these are kind of issues you also have when you do Karo competitions. So you still have some kind of figuring out what model worked. So you don't know the name of the model anymore, what it does. So maybe version controlling, if I had to repeat those things once more. Yeah, so what are the lessons I learned after doing this? One is prediction is very difficult, especially if it's about the future. So, so if you make multiple predictions, it's only the popular ones that will get you to they make you like Nate Silver. Nate Silver, and everyone knows him everywhere. So he predicted Obama's election, and everyone knows him now. So, but he failed in Trump, so people will forget that one soon. So, and then, so now stationarity is just much like, this is just about stationarity, more like the present. So like most time the picture doesn't look very different from the present in some context. So, yeah, so these are some of the, I realized that if you have some irregular time, space data, you may want to use some binning to actually get better aggregation. So, and then choosing the right bin is also another problem. So, but when I was doing some research, I realized there may be a relationship with Nyquist frequency. So, whether I get aliasing or so, I'm not so sure of that. But choosing the right size of bin is an open problem. So, and then, yeah, so there are some issues with time difference models too. And yeah, so, and even in that algorithm, if we look through those RLS implementation properly, we could actually find a way of adding regularizers there too. So those were some parts of the algorithms I saw. If things get wrong, I can add regularizers and make things better. So, and then the Kalman gain is just a form of a damped window too, because that's how you forget the value of things you forget and the ones you retain. So, yeah. Thanks for listening.
Cool. Are you aware of why the uncentered transform is so named?
Oh, I don't know the history behind it, actually.
The guy coming up with it, he came up with it and he decided it was the only one that didn't stink.
So, okay.
I recall reading a paper before Trump elections where they were using Kalman filters for smoothing polls data. Can you comment on that? What exactly, like how do you use it for smoothing?
Yeah, you could. Yeah, it's if you have to tweak your gain values properly. I think the answer lies in the gain value, how the gains are implemented. So you could use it for smoothing too. So I think the answer lies in the gain. So how you set it up. Sure.
So if you had to today try to predict the big, let's say a time series that's difficult, like let's say the Bitcoin one, would you turn to unscented Kalman filters?
Yeah,
would that be your
unscented is
first
the way
stop?
to go, actually. I won't try anyone, actually. So
Thanks.
only as unscented I would use. I won't do any other route. Okay.
Hi. Just had a general question about forecasting, not related to any particular technique. I was just wondering, like, if you're trying to do forecasting and you have a bunch of periods in your time series where your data is corrupted or missing, and say you're trying to predict the latest or the next value in your time series. Are there any good ways to handle that so that you still learn from earlier periods before these gaps happened?
Yeah, I think Kalman filters, because there was a part of the slide that was saying handle some missing data. So because the way Bayesian work, Bayesian stuff, you have a prior, posterior.
Okay.
Even if you put some random values like initialization, it may correct itself in the future. So if you don't have so many missing data, you can actually just generate some random values there, and it will correct itself based on data. So, but there shouldn't be too much of those missing data. If you have a lot of them, then you bias in everything, so you don't have any output.
All right.
Yeah.
Sounds good.
Hey, so I understand that Kalman filter assumes Gaussian distribution for the errors.
Yeah.
That is not the case. How do you correct for heteroscedasticity in the errors?
Yeah, Kalman, uncentered Kalman filters handle that case to, I think, third factors. Because usually if it's stationary, you even correct to even the fifth moment. But when it's non-stationary, it's usually like second, third order by the
Sorry,
Taylor series.
which one?
Uncentered Kalman filters handles those cases.
Okay.
Yeah.
I have another question. Do you know if the type of transformation of like the classic linear regression models for like Price-Winston type models, how do these relate to Kalman filters?
Repeat one.
So there is a type of transformation for linear models where the errors are AR1. It's called Cochrane Orcutt or Price-Winston transformations. I don't know if you're familiar with that and if any of these are actually related to the approach that you're using.
Yeah, it would be because I described some gouge models. Maybe you're talking about those ones. They may look like that. But I didn't go to that. It's a lot of mathematics.
So this model basically, the transformation models the errors as AR1 instead of just assuming they are IID.
Okay, I have not seen that.
Okay, cool, thanks.
So is the Kalman filter giving a prediction for a specific value for the next time step or a distribution?
No, a value.
Okay. Then my follow-up question is, if we really wanted a distribution, would these methods or some variant of these methods help us get that distribution, or would we have to look somewhere else?
No, you could, but I have to think about it in details. Look through the implementation, the papers once more. But there should be a way out for that.
Thanks.
So, okay. So these are my references.
Cool. So I'm hungry. If you want to go get something to eat, we're going to go to Rogue. We don't have an invitation. We're just going to show up and take over the place. So if you want to do that, head over there. It's over by the Waterfront SkyTrain station. But if you would, could you please help put the chairs away? So it's like grab your chair and put on the rack. Oh, in the back. Like that rack.
Give him the microphone.
Yeah, I want to advertise a meetup that I do. Actually, it's on reliable and distributed algorithm. So it's distributed systems algorithm of a meetup. So these are the next ones. So we have one sharing memory. That's this Saturday, and consensus. That's on April the 7th. So you can join us at the library. So I'll make the slides available tonight. Actually, when I get on. Yeah. I'll do that today.
So the folding chairs are the ones that go up to the front there, onto the racks. And the fixed chairs, just keep them off to the side. We've got some tables we have to put in the center. Thank you. I never like these. They're awkward. Yeah. They move around, right?